Hello, welcome you all. I'm Meghamala, working assistant professor from Electronics and Communication Department, Institute of Aeronautical Engineering. And today I'm going to talk about the problem solving on data flow modeling. So far we have discussed about the different problem solvings on different criteria, right? Different levels in the Verilog. So today's topic, we will discuss some more problems about the data flow modeling, the problem solving in the data flow modeling. So we know that data flow modeling is one of the major technology or is major technique where we will implement the designed product, right? So what is a data flow modeling? So data flow modeling is all about, it's just describing the structure of a particular module that you are considering. For example, I'm going to consider from a half adder. So this half adder in the data flow modeling, how can I represent this? I just describe the structure of that particular half adder, right? So that half adder is built with respect to the gate. So the data flow modeling is nothing but it is the abstraction, or else it is the extraction from the gate level modeling, right? So the data flow modeling, for small circuits, the gate level modeling approach works very well because the number of gates is limited and the designer can instantiate and connects every gate individually. So before we move forward to the data flow modeling, let us discuss something about the gate level modeling, right? So gate level modeling is nothing but it is one of the modeling in the Verilog. So this gate level modeling tells us that in order to describe something, or else in order to build some kind of electric circuit, okay, when you are designing some electric circuits, all that we do is with the help of gates we will design the structure, right? So the gate level modeling is nothing but with respect to the gates, different sort of gates. Already the gates are in the Verilog library, primitives, different gate primitives. With the help of different gate primitives, we will be constructing the different modules, different electronic devices, different electronic modules. So the gate, sometimes based on the structure that you are considering, the number of gates may increase, sometimes the number of gates may decrease. So the number of gates are limited. In particular design, the number of gates are limited, whereas in some particular device, the number of gates are unlimited. That means, for example, for complex design that you are considering, for the complex design, we can consider more number of gates. For simple basic designs, we can consider the gates of around 5 gates, like that. So for small circuits, this gate level modeling, gate level behavioral modeling, it approach very well because for small circuits, obviously there is a limited. The number of gates considerations would be very small, whereas for complex design, the number of gates would be more. Then also gate level modeling is very intuitive to a designer with a basic knowledge of digital logic design. So here we are saying that this gate level modeling, so being a designer, if you want to design some circuit, okay, if you are designing some basic circuits and if you are choosing this gate level modeling, then I can tell you that gate level modeling is a basic modeling and it is very easy to construct, right? So it is very intuitive to a designer, that is, it is very easy to consider. It is very apt. It is very easy to consider this sort of gate level modeling. So it is very intuitive to a designer with basic knowledge of digital logic design. So it is I can say that out of 4 level modeling, see, 4 level modeling already we have discussed that behavioral modeling, data flow modeling, gate level modeling and switch level modeling. So as these are the four basic level modeling styles in the Verilog, out of these 4 modeling styles, I can say that the gate level modeling is very easy. It is very easy for any designer. It is very easy to construct the basic building blocks of the electronic devices, right? So however, in complex design, the number of gates is very large. Obviously, if you are based on the structure that you are considering, if your structure is big and large, or else if your structure is enormous number of gates are required, then obviously you need more number of gates. And if your structure is very small and very plain, obviously the number of gates consideration would be very less, right? So the designer, the complex designers, for the complex designings, we need very large number of gates, whereas for simple designings, we need very less number of gates. Then the designers can design more effectively if they concentrate on implementing the functions at a level of abstraction higher than gate level. So after before you design something, you should have a criteria in your mind saying that what sort of level that you are considering, what that you are going to consider. Okay, and what level of abstraction you want to write your code. All such things need to be, you have to plan with all such criteria, right? So here, the designer can design more effectively. When a particular project can be effectively, we can get the output is when a designer, if he has more effectively concentrating more, pondering more on implementing the function of a level of abstraction. See, building certain module is different, and then implementing that module is also a basic thing, right? So constructing a module is obviously it takes very less time, or else based on the structure, based on the level of constructing. If it is a small circuit or else if it is a large circuit, obviously the time constraint will be maximum. Okay, and we need to consider all the aspects. But whereas if you're considering a small circuit, okay, if you're designing a small circuit, then all the parameters regarding the delays, regarding the time constraints, and all things will be they take the time of consumption will be very less. So here, obviously, when you are designing some structure, we will concentrate on the structure, right? We will be concentrating more on the structure. That means number of gates that you are considering. So after forming a structure, the next thing is we are going to implement it. So for this implementation, we will think of different level of abstraction. So this being a designer, it is our responsibility, or being a designer, it is our choice that out of 4 level of abstraction, which level we are going to consider. It is purely depends upon a designer. So here, after forming a structuring, we say that then comes to the implementation. So the implementing the function in the level of abstraction higher than the gate level. So out of these 4 level of abstractions, which abstractions you are going to implement the design structure? That is very important, right? So this is what this sentence says. And then data flow modeling, it provides a powerful way to implement a design. So obviously, after designing or else after making into some structure, then the thing is we need to implement it. That means what we are going to design it properly, or else the implementation occurs in the data flow modeling. So this data flow modeling, it's one of the powerful way to implement a design. So it is one of the powerful way, and also it is one of the easiest way in order to implement certain tasks in the Verilog. Then Verilog allows a circuit to be designed in terms of data flow modeling between registers. So here, this Verilog, it allows the circuits to be designed in terms of data flow between the registers. So here, registers, we are talking about the registers. That means what the data flow, how the data is flowing between the registers. This is what about the data flow modeling. So the name indicates here is data flow modeling. That means what? The data, how the data is flowing between the registers, between the flip-flops. We know that registers are nothing but the group of flip-flops or group of latches, right? So here we will see, we will more concentrating on how the information, or else how the data is transforming, or else how the data is transferred between the registers, and how design process does rather than instantiation of individual gate. So here we will concentrate more about the more on the design process rather than the number of gates used, or else rather than the instantiation of the individual gates. We will be more concentrating on the design process from the gate level modeling, right? Then the gate level modeling has become a popular design approach as logic synthesis tool have become sophisticated. So here we can say that as this data flow modeling is one of the major approach, or else it's one of the good way of communicating among between the registers. So it is one of the good approach that we can consider. But the logic synthesis tools, the tools which we are considering for the simulation purpose or else for the synthesis purpose, are very sophisticated. Okay, the name sophisticated means they are very considered to be the tools, the logic synthesis tools that we are considering are very sophisticated, means they are very case sensitive, right? So the tools we are, if you are considering your data in the data flow modeling, then you have to be very keen enough of choosing the software tools, or else the logic synthesis tools, you have to be very keen enough to know about it. And then this approach, that is data flow modeling, this approach allows the designer to concentrate on optimizing the circuit in terms of data flow. So here what we does is, like the designer, he has to be very concentrated, like he has to be more concentrative on the optimizing the circuits in terms of data flow. So all that we need to do is how the data is flowing between the registers, how the data is flowing among all the different sort of registers with respect to the flip-flops and also the latches, right from the beginning till the end. Okay, right from the top to the bottom, in all the areas, in all the corners of the circuit, we are very much keen enough that how the data is flowing between one register to among the one register and the other registers. It's all about the data flowing among the registers. Then, for maximum flexibility in the design process, designers typically use Verilog description style. Okay, so designers, obviously they use a typical way of describing each and every structure. So they obviously go with this Verilog description style. Why? Because it combines the concept of gate level, data flow and behavioral design. So obviously if you are coming up with some sort of module, then you have to be the implementation part has to be done with respect to the Verilog descriptive style. So this Verilog descriptive style is maximum concentrating, or as a concepts of we see the gate level modeling, the structure which is formed with respect to the gates, and the data flow modeling, the data, how the data is flowing among different registers, and also the behavioral designing. That means how the data is, how the certain equipment, or how the elements are behaving in such particular area. So we will be pondering on all these different styles of Verilog. Then, in the digital design community, the term RTL design is commonly used for combination of data flow modeling and behavioral modeling. So here, in the previous sections, when we are discussing about the module 2, that is data flow modeling, in the data flow modeling, we have come across a concept called RTL. RTL is register transfer logic. So this is register transfer level is nothing but, here we will see how the information is transferred among different registers, right? So different registers, how the data is being transferred. So in the digital design community, we see this RTL based design. Some designs will be with respect to only are concerned with this RTL based, that is register transfer language, and they are commonly used for the combination of data flow and as well as the behavioral modeling. So in this register transfer level modeling, we see this RTL is nothing but it is a combination of data flow modeling and as well as behavioral modeling. Okay. Then, so in this data flow modeling, also we have discussed about the continuous assignment statements. So the statements, this is nothing but the assignment operator, and onto this assignment operator we write the variables, and onto this assignment operator, this is nothing but the assignment operator. On to the right of the assignment operator, we will be writing the expression, right? So here, when it comes to different statements, continuous assignment statements, this is the most basic statement in data flow modeling. So in the data flow modeling, all our statements are basically in the form of continuous assignment statement, and the execution or the synthesis of this continuous assignment statements, they go synchronously. Okay, they go synchronously, and then this continuous assignment statements, they are used to drive a value onto a net. So obviously we have different values. See, this is a net. Net is nothing but the variables where it contains different variables at different names given as A is equals to 1, B is equals to 2, like that, right? So here we will be giving this continuous assignment statement, they used to drive the value onto a net. So this is a net, for example, A. So for this net, I am giving a number or its value as 1. So A is a variable, right? So here we will see that A is equals to 1, B is equals to 2, like that, so and so. So the this assignment statement will help us to drive or else give the values to certain types of variables. And then the continuous assignment statements, they replace gates in the description of a circuit and describe the circuit at a higher level of abstraction. So here, this continuous assignment statements, what they does is, they just replaces the gates in the description of the circuit. So here, for example, if you are talking about the AND gate or also half adder. So half adder consists of AND gates and also XOR gates, right? So here, this continuous assignment statement, what they does is, they just totally replaces the gates. Okay, they just replace the gate and they describe the circuit in the higher level of abstraction. So they just forget about the gates, what sort of gates that you are considered. Okay, they just replace the gates, but they more concentrate on describing that particular circuit. Then this statement starts with the keyword called assign. So if you are considering any half adder, then usually in the data flow modeling, assign is a basic keyword where we'll use. So we will assign y is equals to A dot B. This is how we will write for each and every particular gate. By using the assign keyword, we will be mentioning with respect to the gates that you're considering. And then they present structural connections. So here the data flow modeling is data flow modeling is extracted from the gate level modeling, right? So obviously from the gate level modeling, we got the data flow modeling. So the data flow modeling is nothing but we have these structural connections. We more concentrating on these structural connections. So physically we will connect by a net called via. Okay, physical connection used where we need to connect the different gates is through via is one of the net that we consider in this gate level data flow modeling. Then they are used for modeling tri-state buffers. So here this continuous assignment statements, they use for modeling tri-state buffers, and also they can be used for modeling combinational logic states as well. So not only for the buffer states, they also used for this combinational logic as well, and also they are outside the procedural blocks, always an initial block. So this continuous assignment statements, they are out of always at the rate and initial blocks. Okay, usually we will write a program like this: module, name for module, port list, and then we will initialize the input and as well as the output. So after initializing the output, directly will come across always at the rate. So always at the rate is nothing but it's a keyword where we use when you are considering your program or else your code to be written in the behavioral modeling. In the behavioral modeling, if you're writing your code, then obviously we need to write always at the rate. But here this continuous assignment statements are saying that outside of this always at the rate, we are going to give our statements. Continuous assignment statements are need to be written out of the always and the initial blocks. Okay, this is one of the important point to be remember in the continuous assignment statement. For then the continuous assign override any procedural assignment. So we have different types of assignment statements: procedural assignment statements, implicit assignment statement, explicit assignment statement, and continuous assignment statement. So if you compare all these four statements, we are saying that this continuous assignment statements, they can override the procedural assignment statement. And then the left hand side of continuous assignment statement must be net data type. Okay, yesterday we have discussed few data types. So obviously on to the left of the left hand side of the assignment operator, the right hand side should be expression and left hand side should be variable, and that variable it could be in terms of data type or nets, right? So we'll see the examples with the examples, and now we will see this syntax followed with respect to the strength and delays. So strengths and delays are one of the important topic that we have discussed in data flow modeling. Strengths are nothing but based on the number of gates that you are considering, the strength is to be calculated. Okay, delays are nothing but with how much of delay the input output is observed. Okay, so this is the difference between the strength and delays, and here goes with an example of 1-bit adder using continuous assignment statement. So using the continuous assignment statement, this is an example with 1-bit adder. Okay, so here how goes the syntax is: assign strength strength, and the delay as well, net, which is equals to expression. So this is an assignment operator, and on to the right we have expression, and on to the left we have data types or net data types, right? So here we will see in the example, module adder. So the module that we are considering is 1-bit adder. So our name should be adder using assign, register A and B, okay, A and B, and wire some carry. Wire is meant for the physical connection between the A and B, right? So A and B, and my output is sum and carry, and assign with 5 nanoseconds of delay. I am observing that sum and carry, okay, sum and carry, which is A plus B. Okay, adder itself is nothing but we are going to add both A and B, right? So A plus B. And now initial. So as I said the continuous assignment statements are written outside of the initial block or else the always at the rate block. So always at the rate or initial block. So out of this context, out of these two, the continuous assignment statements are to be mentioned. So these are nothing but the continuous assignment statement, And now we have started initial begin, and this is about the monitor, just to display purpose. So with 10 nanoseconds of delay, A is equals to 0 and B is equals to 0. And for 10 nanoseconds of delay, A as 1, B as 1. And obviously after 10 nanoseconds of delay, A, B as 0. And finally finish and end module. Okay, so one thing you have to remember when you're writing your code in terms of continuous assignment statement is out of the context, out of this initial block and also the always at the rate block, the continuous assignment statement should be written. Okay, and then finally end module, end module. Then we will see one more example, that is a tri-state buffer using continuous assignment statement. So how can we write the code with respect to the tri-state buffer? By using continuous assignment statement. So module, the name of a module is tri-state buffer. Register data in variable, in enable, data in enable, and wire pad. Then see, this is a continuous assignment statement. So we are assigning pad as enable and data in 1 bit of information, right? 1 bit of data. So here you can say that this is a conditional operator, right? So in the operators, we know different types of operators, logical operators, bitwise operators, and we have conditional operators as well. This conditional operators will help us to know whether the condition is true or false. So here we know the tri-state buffer. Tri-state buffer is nothing but when the output is 1, when the input is 1, output obviously goes 0. That means when the input is true, output goes to false. When the input is false, output goes to true, right? So that's the reason we are considering the conditional operator enable data in 1 bit. Then finally enable, if enable is 0, what happens is data in as 1, and if enable is 1, data in as 0, right? When enable is 1, data as 0. When enable is 0, data as 1. Then finally finish and end module. So these are the very basic and simple examples to write that when you have come across a question based on the continuous assignment statement with respect to the tri-state buffer, right? Then quickly we'll move forward talking about the propagation delay. So what is this delay? Already we have discussed delay. Delays are nothing but they are concerned with respect to the time, right? So when you are writing the code, we will mention the delays in terms of ASH, right? 10 nanoseconds of delay at input or output, whatever, wherever we are observing, right? So here, this continuous assignments may have a delay specified. So in the previous example that we have considered in the tri-state buffer, for each input, the 10 nanoseconds of delay is observed. So the continuous assignment statement, they can specify at any time, and only one delay for all transactions may be specified, right? So here if you observe only one delay, right? So here only one delay, 1 nanoseconds of delay is observed for all the transactions, right? So we can say that there is no, the delays cannot be switches and they can be at once, one as well. So the minimum, see, this is an example where we see the maximum delay range may be specified. So my example is about tri-state buffer. Again, module using assign delay, registers in wire pad, and assign delays of 1, 2, 3. That means we are considering 3 delays. Delay 1, delay 2 and delay 3. So, initial for 10 nanoseconds of delay 0, 1 and 1, 0 and 0, 0. And then end module. So, this is a basic example based on the propagation delay. And now we will see the gate level modeling becomes very complex for VLSI circuits. Hence, data flow modeling became a very important way to implement the design. So we know that in the Verilog, where the data flow gate level modeling become very complex for the complex designing purpose, and such we are switching on to this data flow modeling, where here in the data flow modeling we are only concentrating on the structure of that particular module. And then in data flow modeling, most of the design is implemented using continuous assignment statement. So in the data flow modeling, maximum times we will write our code, or else we will implement that particular module in terms of continuous assignment statements only. Okay, why? Because here we can drive the value onto a net. So there is a possibility of giving some values to a variable, right? And then this continuous assignment statements, maximum we will use a keyword called assign. And also there are very little changes when you want to do data flow modeling in comparison to gate level modeling. So if you want to compare the gate level and data flow modeling, only few little changes can be considered, can be made. And so here with one more example, we can say, see, this is an example. So this example is talking about, see, here we have AND gate, and this is a NOT gate, and here we have a OR gate, right? So this is a small example where we have the input A, B, C as input and D, E as the output. So here if you see input A, B, C and output D, E. So this example is all about the continuous assignment statement by considering the continuous assignment statement. So here what am I doing is I need to assign, or else I need to get the output, or I need to write the expression in terms of continuous assignment statement, such that for E, for output E and for output D, how can I write is with the help of this gate level. Basically, I can say that this is a gate level modeling. So onto this gate level modeling, I am just comparing it with the data flow modeling. That is, how can I write the, how can I code the problem, or else how can I write in terms of code the gate level modeling, how can I describe in form of a structural description of a particular module. So this is a gate level modeling, I can say, and the code is all about the data flow modeling, how the data is flowing among all the different gates. So here only first initializing all the inputs and outputs, and then writing the continuous assignment statement. So when I write continuous assignment statement for E, output E, assign E is equals to, all that I can say is negation of C. Why? Because here we have a NOT gate, right? So NOT gate is negation of C. And then this, if it is 0, obviously I can get here as 1. So negation of C. And then assign D. So for this D output, how can I write? I can write as it is an AND gate, A and B, and then OR E, right? A and B and then OR E. See, this is a OR gate, right? So this is a OR gate, and this is a AND gate, and this is a NOT gate. So for E output, I'm writing, or else I'm in the data flow modeling, I can write A and B or E. And finally, end module. So here my module, I've started with the keyword module, and then finally I'm ending up with the keyword end module. Okay, so this is a small example this is a small example which says that how can we write a gate level, or else how can we differentiate, or else how can we compare a gate level modeling and a data flow modeling. So I hope you all understand today's topic, the basic examples based on the continuous assignment statements in terms of data flow modeling. Okay, so in the exam point of view, if you come across any question saying that write a program based on using continuous assignment statements, means simple way you can consider the tri-state buffer. Okay, the tri-state buffer is an example, and also you can consider one bit adder example as well. So these are very easy to write, and these are very easy to implement as well. So I hope you all understood today's topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.